Hello. Today we're going to start with Chapter 5, our study of exponential and logarithmic functions. And so if we consider these two functions, f of x being 2 to the x and g of x being x squared, one big difference we can see is the place where x is. For f, x is our exponent. And for g, x is our base. Right? They're two completely different spots for x to be in. And f is exactly what we'd call an exponential function, where our variable, our x value, is the exponent. Right? So we can define an exponential function of this form, b to the x, where b is positive, and we don't want b to be 1, right? Because 1 to the x for any power would just be 1. That would be boring. Right? We call b the base. And what we notice is we're going to have functions that look like 3 to the x or 1/2 to the x, right? We're going to have lots of things with exponents. And what's nice about the study of exponents is all of these properties that we had before, right? The same normal few properties, basically 1 through 5, they're all going to hold without exception. And all the exact same things, that'll be fine. The two properties that we're going to take advantage of, mostly right now is 6, is the fact that if I have equal bases with two different exponents, that those exponents actually must be the same. Or if I have two different bases raised to the same exponent, those bases must be the same. Right? So since this is a new type of function, we can actually study new type of equations in trying to solve for x. Okay, here we want to solve an exponential equation. 2 to the x minus 3 is equal to 2 to the 4x plus 1. And we had a property that said if a to the m is equal to a to the n, right, where our bases are the same, then those exponents actually had to be equal. So that's exactly what we're going to do. We have equal bases, so what we can say automatically is those exponents must be equal. All right, and we've turned this weird exponential equation into a standard equation that we could solve, right? And we're going to subtract an x. Negative 3 is equal to 3x plus 1. I'll subtract a 1. Negative 4 is equal to 3x, and I'll divide by 3. Negative 3/4 is equal to x. We can solve slightly more difficult problems where our bases are not quite the same. Here's an example of a slightly more difficult problem where our bases are not exactly the same, right? I can't use that really nice property a to the m is equal to a to the n, then my exponents are equal, right? I don't have equal bases. So what we want to do is we want to reduce bases. We want to think, can I write 9 and can I write 27 as powers of the same base, right? Is there something that goes into both 9 and 27? And of course, we can think of 9 as 3 squared, and we can think of 27 as 3 to the third. So we can transform our original equation into something like 3 squared to the 2 minus x is equal to 3 cubed to the x plus 6, right? And still, our bases are not quite the same. We still have 3 squared raised to a power, or 3 to the third raised to a power. But like we said, all of the same powers or properties of exponents still hold. So if I have 3 squared raised to a power, that property said I just multiply that exponents together. Likewise, if I have 3 cubed all to the x plus 6, I can just multiply that power of 3 with the power of x plus 6. Right? Now, I actually have 2 equal bases, and now I can automatically say that their exponents are going to be equal. Right? And I can solve this problem. I can subtract 3x from both sides. I can subtract 4 from both sides and get x is equal to negative 14/5. we can look at the graph of a basic exponential function, right? This would be the graph of y is equal to 2 to the x. And they have really nice properties, right? One we can see is, like listed, it's continuous and it's a smooth curve. If we look at f of x, it actually is a nice kind of curved line there, right? One thing that's always true is it will intersect the y-axis at the point 0, 1. Right? That will always be a point on the graph. Another point that's going to be common is a little bit more of a formula. In this graph, it intersects the point at 1, 2. But if we have a slightly more abstract function, like y is equal to b to the x, what will happen is the 2 points on the graph that will be the same will be 0, 1, and 1, b. Whatever that base is, the graph is going to cross that same base value b when x is equal to 1. Right? One other nice property we have that's listed below is we're going to have a horizontal asymptote right here. Right? This is one of these weird cases where the asymptote doesn't actually deal with fractions, but deals with the value or how the function works. Right? If I want y to be 0, it's like asking us a question, what power should I raise 2 to get the number 0? And it turns out that nothing here works. So in fact, y can't ever be 0, which is kind of like a weird other reason why we have this asymptote there. All right, one thing we're going to do is talk about a base that keeps coming up time and time again. Okay, one number that we actually see repeated a lot is the number e. It shows up a lot in actually real-world examples, whether it's in nature or business or anything like that. E actually shows up a lot, right? It's weird because it's an irrational number, so it's not exactly any fraction. And so what'll happen is we'll commonly have a function like e to the x, right? That'll happen a lot, and eventually when we get to it, it'll have a very common log base e. But again, that will have to wait for its own lecture. One of the most important applications to exponential functions is what we call compounding interest, right? This really rules our lives in the examples of banking or loans, right? And we'll go through examples of all of these as we move forward. But what we want to understand is this will help us compute how much money is in an account after so long of a time has happened. So the principal is how much we initially invest, right? So if our initial investment or in principal is invested at a rate of R%, compounded n times per year. What that means is after so many days or months or weeks or whatever, an interest gets accounted for and the money increases, right? This helps us grow our money in terms of a bank savings account, or it hurts us in the way loans do, where interest will actually increase the amount of money we owe. So it turns out if the interest rate R is compounded n times per year for t years, the money in the account is given by this formula, right? What's important to remember is n is the times per year, right? So we can have things like if it's annual, right? N is going to be 1. If it's monthly, right? N is going to be 12. If it's daily, N is going to be 365, and so on. And so what we can do is actually think of a real-world example of how this might help us. One of the questions we want to answer is why might this compounded interest equation be useful? And the answer, of course, is in figuring out loans. So for example, we want to save for a down payment that we're of a house that we're going to buy in 6 years. And we have $3,500 to invest today. So we go to two different banks. PNC will offer an account with 4% interest compounded monthly. Bank of America, on the other hand, will offer you a slightly lower rate, at 3.75%, but it will compound your interest daily. And the question is, which bank will give you the most money? Which bank will you want to put your money in? Right? Of course, for both, we're going to use the formula A is equal to P1 plus R over N to the NT. This is our compounded interest N times per year. So let's break this problem up. Right? We can talk about Bank of America and then PNC. So let's see. For Bank of America, right, we're investing $3,500. 1 plus our interest rate is 3.75%. So I want 0.0375. It's compounded daily, so that N is 365. And it's N 365 times 6 for 6 years. Right, we'll just move PNC over here. Right, and if we start to compute that, 360. Right, the first thing we'll do is figure out what that weird exponent is. 5 over 365. That turns out to be 2,190. Right, this represents actually the number of days. So let's see. What we'll do is we'll compute this whole quantity. 365. We put that into our calculator, and we'll get 1.252. And when we multiply them together, our account in Bank of America will be a grand total of $4,383.08. Right? This isn't how much more money we have. This is how much total money we have. So we make close to $900 for just saving the money and not doing anything. It's a pretty good deal. Let's see, for PNC, we'll have the same investment, right? $3,500. Except now they're going to give us 4% for compounded monthly. So 12 times 6, 3,500. 1 plus 0.04 over 12. 12 times 6 is 72. And again, we'll compute that tail end of the equation, 3,500. And I get 1.2707. And when I compute that, I get a grand total of $4,447.60. And so if we look at these two examples, clearly we're going to go with PNC because at the end of our time, at the end of our 6 years, we have more money in our account. Right? This original formula, we have our interest compounded N times per year. Right, so we have an N and we have two N's in our equation. And this is what we call discrete computation, right? Where there are breaks that we have to wait for, right? We have to wait for one day to happen until the computation of the interest can happen again. Sometimes we can have what's called continuous or like continuous. For example, we might have a trading scenario where a trade might happen in a fraction of a second. And if you count all of the fractions of seconds within a whole year, you might as well have that be a continuous amount of trading or continuous amount of compounding interest. So that's exactly what we have. We have interest that can be compounded continuously. And it turns out when we throw out that N condition, N times per year, and say it's just continually compounding, our formula gets a little bit simplified, right? If our initial investment P, our principal, is invested at an interest rate of R compounded continuously, then after T years, the formula for the money in our account will be given by A is equal to P times E to the RT. Right? Notice because it's continuous, there's no need for an N. There's no need for a how many times per year. The interest is continually growing. So let's say, for example, we have our two banks from before, and let's remember, PNC, our account was $4,447.60, and for Bank of America, our account was $4,383.08. So let's say now Quicken Loans is trying to be competitive. So they're going to offer the second highest interest rate of 3.95%, and they'll say they'll compound it continuously, right? So before PNC was our winner, does this change our decision? Will this give us more money in our account than PNC? So let's see. I get A, P, and because it's continually, I can use E to the RT, right? This is going to be 3,500 E to the 0.395, that's our interest rate, times 6. How many times per year? Now we can do this single calculation in our calculator, and we'll get $4,436.04. So it turns out that continually compounding interest doesn't mean we get an infinite amount of money. There still is a limit, right? This is how much money we have in our account. And to answer our question, no, we still stay with good old local PNC. All right. Hopefully this was helpful, and we see why exponential functions are worth studying and how important they can be. I will see you all in class.